welcome to this session. Now, in the last class we were solving the a three-dimensional problem in spherical polar coordinate system, and we have completely we are using the separation of variables, and we have formulated the eigenvalue problem in the phi direction, because there was no phi symmetry in this particular problem, and we have seen the eigenfunction is constituted by the sine function by a combination of linear combination of sine function and cosine function, and the corresponding eigenvalues are the natural number including 0. So, then we formulated the problem into the we divided the problem into radial direction and the theta direction, and we have formulated the eigenvalue problem in the theta direction, and we were solving in the halfway of the eigenvalue problem in theta direction. Now, in this class we will be solving the problem completely. So, we have seen that in the last class that the governing equation in the theta direction is nothing but d theta of sin theta d theta plus m square sin square theta plus lambda square theta is equal to 0 is the governing equation. Then we substitute cosine theta is equal to t, and let us see what d theta dt in terms of theta. So, in terms of t. So, d theta dt, what is d theta? D theta. Okay. So, d theta dt d theta. So, dt d theta will be nothing but minus cosine theta minus sin theta. So, it will be minus sin theta d theta dt. So, I am expressing in terms of the transformed coordinate system t. So, sin theta d theta dt will be nothing but minus sin square theta d theta dt is minus 1 minus t square d theta dt. So, therefore, d theta of sin theta d theta d theta so it will be d theta d theta. Okay. This will be nothing but d dt of minus 1 minus t square. I am just substituting this here, 1 minus t square d capital theta dt, and d theta. So, I expressed by d dt. So, it will be there will be dt d theta here, and dt d theta will be nothing but minus sin theta as per its definition. So, this becomes d dt of 1 minus t square, the minus will be consumed, d theta dt, and this will be sin theta. Okay. So, we will be having 1 over sin theta d theta sin theta d theta t theta is equal to d dt of 1 minus t square d theta dt. Then I substitute this equation into the governing equation here, and let us see what we get. If we really do that, then we will be getting 1 over d dt of 1 minus t square d theta dt plus m square 1 minus t square theta plus lambda square theta is equal to 0. Now, this is nothing but the Legendre equation of nth order. So, this will be nothing but the nth order Legendre equation if lambda square is equal to n into n plus 1. Okay. So, if we put lambda square is equal to n into n plus 1, then this will be nothing but the nth order Legendre polynomial, and n is nothing but m plus 1, m plus 2 up to infinite terms, where m is basically the eigenvalues that we have already talked about in the whenever we were solving about the phi direction. So, m was running from 0 to infinity. So, eigenvalues were lambda square is equal to n into n plus 1, where n are m plus 1 up to infinity. And what are the eigenfunctions? Eigenfunctions will be the combination of Legendre function, Legendre polynomial and Legendre function. So, theta of t will be nothing but C1 P n m t plus C2 Q n m t, and in terms of theta. So, t is equal we put theta in terms of small theta is nothing but C1 P n m cosine theta plus C2 Q n m cosine theta. And we already know that for t lying between minus 1 to plus 1, Q n is unbounded at t is equal to plus minus 1. So, therefore, the whole solution is bounded, therefore, the associated constant has to be equal to 0. In order to satisfy this boundary condition, C2 has to be equal to 0. So, therefore, the eigenfunction will be nothing but the Legendre polynomial. So, theta as a function of theta will be is equal to C1 P n m cosine theta. These are the eigenfunction in theta direction. Now, we have already almost solved the problem. Next, we will be solving the r direction. So, if you look into the r direction, the r varying part will be nothing but minus 1 over r d dr of r square dr is nothing but minus lambda square is n into n plus 1. So, we have d dr of r square dr minus n into n plus 1 r is equal to 0. So, this becomes the governing equation in the r direction, and if you really look into this particular governing equation, then we can identify this is nothing but an Euler's equation. So, this will be nothing but Euler's equation. So, if you just open the differentiation, you will be getting r square d square r dr square plus 2r dr minus n into n plus 1 r is equal to 0. So, this is the Euler's equation, and the solution will be in the form of r to the power alpha. So, if you just put r square dr will be nothing but alpha r to the power alpha minus 1, and d square r dr square will be nothing but alpha into alpha minus 1 r to the power alpha minus 2. So, it becomes r square into alpha minus 1 r to the power alpha minus 2 plus 2r dr will be alpha r to the power alpha minus 1 n into n plus 1 r to the power alpha is equal to 0. So, this becomes alpha into alpha minus 1 r to the power alpha plus 2 alpha r to the power alpha minus n into n plus 1 times r to the power alpha is equal to 0. So, r to the power alpha will be cancelled from all the sides. So, you will be getting a characteristic equation in alpha, which will be nothing but a quadratic in alpha. So, I will be getting a characteristic equation in alpha. So, it is nothing but a quadratic alpha into alpha minus 1 plus 2 alpha minus n into n plus 1 is equal to 0. So, you will be getting alpha square plus alpha minus n square minus n is equal to 0. So, alpha square minus n square plus alpha minus n is equal to 0. So, alpha minus n into alpha plus n plus 1 is equal to 0. So, we have two roots of alpha, alpha is equal to n and alpha is equal to minus n plus 1. So, I can get the solution of this Euler's equation, and R m n will be nothing but C 1 m n r to the power n plus C 2 m n r to the power minus n plus 1. And if you look into the boundary condition that r is equal to 0, my solution is bounded. So, therefore, if I put that condition here in this governing in the solution, then the associated this term becomes unbounded. For r at r is equal to 0, capital R m n is bounded, or it will be having a finite value. Therefore, this term becomes infinite or unbounded. So, the associated constant must be equal to 0. So, the solution becomes R m n is equal to C m n r to the power n. So, that is the solution of radial varying part. Now, we are in a position to construct the complete solution, and let us construct the complete solution. So, we will be having two standard eigenvalue problem in this particular situation. One is in the phi direction that we have already seen. The eigenfunctions are a m sin cosine phi plus b m sin phi sin m phi, where the m runs from 0 to infinity, and the in the theta direction we had the Legendre polynomial is the eigenfunction, and the eigenvalues are m n into n plus 1, where n runs from m plus 1 up to infinity. So, the complete solution will be in the form of r theta phi is equal to, there will be two summation, because we are now dealing with two independent eigenvalue problem. So, one is m is equal to 0 to infinity, another is n is equal to m to infinity, r to the power n p n m cosine theta multiplied by C m n sin m phi plus d m n cosine m phi, and the constant associated with r that will be incorporated into the constants of phi varying part. So, we will be having the new constants of integration C m n and d m n. Now, these two constants will be evaluated by using the orthogonal property of the eigenfunctions. To be evaluated by exploiting the orthogonal properties of eigenfunctions. So, I am just writing the final solution. We have done this exercise several number of times. So, these will be nothing but phi is equal to minus pi to plus pi, theta is equal to from 0 to pi, p n m square of that of cosine theta sin theta sin square m phi d theta d phi, and again from minus pi to plus pi, 0 to pi, f theta phi. F theta phi is the condition at r is equal to 0, at r equal to 1. So, it will be utilizing, we will be getting this from the boundary conditions using the unutilized condition that at r is equal to 1, your u is equal to f of theta phi, some initial condition at some prescribed function of known function of theta or phi, or in general it will be a function of theta and phi, or it may be a function of theta alone, it may be a function of phi alone, it may be a function, it may be a constant. So let us put it as a general function of theta and phi at boundary condition at r is equal to 1. So utilizing that will be and then will be so we'll be putting the value. So I omitted a step in between. So it will be f of theta phi should be is equal to this. Okay, let me put it that way. So at r is equal to, so I will be evaluating the constants Cmn and Dmn by putting at r is equal to 1, u is equal to f of theta and phi in general. So if I put that in the governing equation, then this becomes f of theta and phi is equal to double summation n is equal to m to infinity, m is equal to 0 to infinity, and r is equal to 1. So that will be gone. So p n m cosine theta multiplied by c m n sin m phi plus d m n cosine m phi. So now the constants Cmn and Dmn will be evaluated from the by exploiting the orthogonal property of the sine functions and cosine functions. So these will be now evaluated by orthogonal properties of eigenfunctions. So I will be directly now writing the governing final solution. So we have done in umpteen number of times. So Cmn now becomes phi is equal to minus pi to plus pi, theta is equal to 0 to pi, p n m square cosine theta sin theta sin square m phi d theta d phi, and in the numerator we will be having minus pi to plus pi, 0 to pi f of theta phi p n m cos theta sin m phi sin theta d theta d phi, where sin theta is the weight function appearing in both denominator and numerator, and your dmn becomes minus pi to plus pi, 0 to pi, p n m square of that cos theta sin theta cos square m phi d theta d phi, and here it will be minus pi to plus pi, 0 to pi f of theta phi p n m cos theta sin theta cosine m phi d theta d phi. So that gives the complete solution of spherical polar coordinate problem in 3-dimensional. And since we have broken down, there are two independent eigenvalue problems existing in this physical situation, we will be having a double summation, and there will be two index m and n corresponding to each eigenvalue problem. So we have really come down to the end of our course, and now I will be so let us summarize whatever we have done. We have looked into the operator and their certain definitions, and then we have looked into the properties of Sturm-Liouville problem and how to obtain the adjoint operator. and then we have looked into the various properties of a Sturm-Liouville problem and established that what is the definition of a standard eigenvalue problem having infinite number of eigenvalues and the eigenfunctions will be orthogonal to each other. We have proved these specific properties of the Sturm-Liouville problem or the standard eigenvalue problem. Then we have earlier we have defined the classifications of the partial differential equations, how to evaluate the parabolic, hyperbolic, elliptical different types, and then the different kinds of boundary conditions we have discussed with, and also we have looked into the system that how to break down the problem into sub problems if we have the number of non homogeneities in the boundary condition and the initial condition. Then we have looked into the all kinds of problem in rectangular coordinate system, parabolic, hyperbolic and elliptical, and also a 2-dimensional problem, 3-dimensional problem and 4-dimensional problem in rectangular coordinate system. Then we moved ahead with the cylindrical polar coordinate system and solved a 2-dimensional problem as well as 3-dimensional problem. Then we have moved over to the spherical polar coordinate system and looked into the solution of 2-dimensional and 3-dimensional problems, which are quite common in various engineering applications. Now, what we will be doing, we will be taking two big example of an actual real problem, which will be effectively a 3-dimensional problem, and will be going ahead with a complete solution of that. So, let us look into a 3-dimensional problem, heat conduction problem, which will be a real problem, actual life problem, 3-dimensional heat conduction problem. In a rectangular coordinate system. So, there will be, it is a 2-dimensional transition problem. So, 2-dimensional in space, 1-dimension in time. So, if you look into the governing equation, this becomes rho Cp del t will be nothing but k times del square t. In fact, it will be kx del square t del x square plus ky del square t del y square, and we assume that thermal conductivity is isotropic. It is same as all directions. So, it will be rho Cp del t will be nothing but k del square t del x square plus del square t del y square. So, if I divide by rho Cp, this becomes thermal diffusivity. So, del t will be nothing but alpha del square t del x square plus del square t del y square. So, alpha is known as the thermal conductivity. Okay. Now, let us put the boundary conditions at x is equal to 0. Let us have the Dirichlet boundary conditions for all the directions. So, t is initially t naught at t is equal to at t is equal to 0, t is equal to t naught for all x and y. Now, at x is equal to 0, let us say t is equal to t01, at x is equal to a, let us say t is equal to t02, at y is equal to 0, we have t is equal to t03, and at y is equal to b, we have t is equal to t04. So, let us have a general problem which will be having all boundary conditions there we are maintaining at different temperatures located at x is equal to 0 and x equal to a, y is equal to 0 and y equal to b. All the 4 boundaries we are maintaining 4 different temperatures, which is basically nothing a special form of which will be nothing but the Dirichlet boundary conditions. And at time t is equal to 0, we had some initial temperature, and on all the 4 boundaries we are maintaining 4 different temperatures. Now we will be looking into the solution of this particular problem. Now, as we have seen earlier, let us count how many non-homogeneities we are having in this particular problem. So, number of non-homogeneities will be, there will be 4 non-homogeneities appearing in the 4 boundary conditions and 1 non-homogeneity appearing in the initial conditions. There are 5 sources of non-homogeneities we have in this particular problem. So, we will be now what we decided earlier, that we can reduce the number of non-homogeneities by defining the non-dimensional independent variable. Independent variable is temperature in this case. So, we can define a non-dimensional temperature such that like T minus theta is equal to T minus T01 by T01. So, this will be basically a in this non-dimensional temperature we can reduce the at least one non-homogeneity in our system. So, we can then talk about instead of 5 non-homogeneities, we will be having 4 non-homogeneities in this particular problem. So, we will be reducing one non-homogeneity, and that will be decreasing the rigor of the solution. So, if we do a proper non-dimensionalization, for example, if we define theta is equal to T minus T01 divided by let us say T01, then and we define let us say x star is equal to x by a and y star is equal to y by b, then x star will be varying basically from 0 to 1 and y star will be varying from 0 to 1. So, if we do that, so it will be getting del theta del t is equal to alpha del square theta square del x star square plus del square theta b square del y star square. So, we will be having del theta del t is equal to, we take alpha a square outside. So, alpha a square del square theta del x star square plus a square by b square del square theta del y star square. So, this becomes a square by alpha del theta del t is equal to del square theta del x star square plus k square del square theta del y star square. Now, what is k square? K is nothing but a by b. This is sort of aspect ratio. This is a non-dimensional aspect ratio. This is non-dimensional. So, left hand side all the 2 terms are the right hand side the term is non-dimensional, the second term, the first term is non-dimensional. On the left hand side theta is non-dimensional. So, therefore, T alpha by a square will be non-dimensional. That means, a square by alpha will be having a unit of time. So, if you really look into that, a square by alpha, a square is meter square and alpha will be having a unit meter square per unit time. So, it will be having a unit of time. So, they will be identical. So, tau will be we define as T alpha over a square is the non-dimensional time. So, we make the system non-dimensional by del theta by del tau is equal to del square theta del x star square plus k square del square theta del y star square. So, this is the entirely the non-dimensional version of the governing equation. Now, our work is next is to make the boundary conditions to be non-dimensional. So, at t is equal to 0 means at tau is equal to 0, my t is equal to t naught. So, my theta is equal to t naught. So, this will be t naught minus t01 divided by t01. So, I call this as theta naught. At x is equal to 0 means at x star is equal to 0, t is equal to t01. So, theta will be is equal to 0, and at x star is equal to a, that x is equal to a, that means x star is equal to 1, theta is equal to t02. So, t02 minus t01 divided by t01. So, this will be theta 1. At y star is equal to 0 means y star is equal to 0, theta is equal to t03. So, t03 minus t01 divided by t01. So, I call this as theta 2, and at y star, y is equal to b means y star is equal to 1, my theta is equal to t04. So, t04 minus t01 divided by t01. So, this will be equal to theta 3. Now, if you look into this system, I have now let us identify how many non-homogeneities are present. Non-homogeneities are 1, 2, 3 and 4. So, instead of 5 non-homogeneities in the original system, now after non-dimensionalization, we have reduced one non-homogeneity. Now, we will be having 4 non-homogeneities in our system. So, next, as we have discussed earlier, we have to divide this problem into 4 sub problems considering one non-homogeneity at a time. So, I stop here in this class. We will take up this problem in the next class and solve this problem completely. Thank you very much.